Let's do that.
Thank you very much, Seamus, for coming to present to us. So Seamus is from the University of Nottingham and he's come to give a presentation to us about storage of energy for our energy CDT, which I know some of you are not necessarily strictly part of, but it's all energy that goes on within the university. And so these are seminars every Friday we have for the energy CDT, which is part of Durham Energy Institute. And it's a very broad energy mix of people across the university. So we have anthropologists, our current executive chair is an anthropologist, but then we have geography, we have the engineering, we have earth sciences, we have physics, chemistry, that kind of dip their toes in as needed, which is what makes it quite a really great diverse community, and the energy CDT very much embraces that. So we're very much looking forward to your talk. So thank you very much, Seamus.
Thanks very much, Stuart. So as has been said, my name is Seamus Garvey. I'm a professor, part-time professor at the University of Nottingham. I was full-time until a year and a bit ago, and what I'm doing with the other 40% of my time that the university doesn't pay for is developing energy storage solutions that will make a difference. And sometimes I say at the start of a presentation that whenever anybody asks me to give a presentation, my answer is simply yes, and then we work out the times. And in this case, I didn't even get asked. I invited myself. Through a conversation that I had with Simon Hogg, who is a professor here and has some similar backgrounds to me. So I'm going to talk today about energy storage with high penetrations of wind in the UK. You probably know that wind is the UK's really big, really important energy resource. Well, I hope you accept that that's at least plausible. And my name is Seamus Garvey, and my initials are SDG, by the way, so I am the original SDG, which also happens to have been acquired by Sustainable Development Goals. And that's supposed to be...
You're leading the way there.
I am. And most of what well, the first part, I'm basically going to talk in two parts, and I'm going to talk for about 25 slides and then stop and see if anybody's got any questions there. And the first 25 slides are about how do we model what's going to happen in the UK as we move towards net zero. And I'm going to draw heavily on a report that was issued in September of last year by the Royal Society. And I had a small bit to do with that report. And the report was called Largescale Electricity Storage. And the link to that report is in this presentation. And by the way, I'm leaving the presentation with you in case that's of interest to you to access, so you can click on that link later on. The Royal Society report effectively said, or posed the question, can we run the UK on renewables? And answered the question with yes, and it's in fact quite affordable to do that. And the report took a baseline case where it simply said, well, let's consider using hydrogen to match up supply and demand. So we all know that the sun doesn't shine all the time, the wind doesn't blow all the time. And when it's not blowing, wind isn't blowing and the sun isn't shining, then you need to have some way to supply energy. And the Royal Society report focused for its base on the idea that that matching up would be done via hydrogen. And in that baseline case, it proposed that we would generate approximately 1% more electricity in every year than we consume. And the reason for that is some of the generated energy you would just throw away, because it's actually the cheapest thing to do is to generate slightly too much. And who cares if the wind is very intense sometimes and we're not able to use all that energy? It's okay to throw a little bit of it away. And it's economically the optimal thing to do. And the other, that's about 15% of overgeneration you would throw away. And the other 15% would be in losses occurred through storage, because when you store energy, you lose some of it. And the Royal Society said we should approximately mix wind and solar in the proportions 80-20. And the reason for that is wind blows more in the winter than it does in the summer, and sunshine happens more in the summer than in the winter. And our electricity demand has a winter bias to it. We consume more electricity in the winter than we do in the summer. So we want a profile that's more rich, more energy in the winter and less in the summer. And so it turns out about 80-20 is approximately right. And the Royal Society report said we need about 44 days worth that's a sort of minimum possible level of storage, 44 days worth of energy in caverns, of electricity output, that is, in caverns. And the amount of power that you need for both the input and the output are both very similar to the sort of values that we would expect. The mean generation from wind power and solar power is approximately what the input power for the storage should be, and the output power is about the same as peak consumption, because there could be times when there's simply no wind and no sun, and we need to take all of our electricity out of storage. And the table in the bottom is something I'm going to develop a little bit further. We can't predict the future very well, but all the indications are that renewable energy has been becoming cheaper, with a small exception recently, and it is looking like in the future, averaged out between wind and solar, we will be paying somewhere between 35 and 45 pounds per megawatt hour for renewable energy. And these are in 2012 numbers, by the way. These are 2012 pounds, because that's the basis for the contracts that are let out, but somewhere between 35 and 45. And depending on what you assume there, if it was 35, then the total amount of money that it would cost us for every megawatt hour that went onto the system, including the storage, is 57 pounds. And if it was, so you see, as we pay more for renewable energy, we have to pay more for, in total, to include the renewable energy plus the storage. But these are very moderate numbers. These are not big numbers for the energy. And for calibration, in all of 2022, the wholesale electricity price was more than 200 pounds per megawatt hour, because we had this energy spike due to Ukraine. And some of the things that the Royal Society report picked out, well, the biggest thing it picked out is that if you want to understand the system properly, you have to look at what will happen over a very long period of time. It is not sufficient to simply look at 1 year. And most of the other studies that inform government policy right now only deal with 1 year. And they say, well, we'll pick a bad year for wind. You know, we'll pick a year that's got low wind, and that is simply wrong. It's not sufficient to do that. You have to pick a continuous series of 37 years. And the report was primarily written by Professor Sir Chris Llewellyn-Smith, who is absolutely firm about this point, that if you study too few years in sequence, you get completely the wrong answer. So this is a graph directly from the report, and you see that if you only studied 23 years, you would assume that about 30 terawatt hours of storage was plenty to be getting by. But if you actually take the full span that the Royal Society report did take, it's clear that you need much more storage than that. Now, just for calibration, a terawatt hour is about the amount of electricity that we use in 1 day in the UK at the moment, and we will consume more in future. So in the future, we'll consume probably twice as much as that. And communication with the Met Office indicated that, in fact, even 37 years isn't enough to look at, that we should be looking at more than 60 years of weather. So the kind of findings are that we need many tens of terawatt hours. If you look at all the energy storage that we have in the UK at the moment, well, I wonder whether anybody knows, would anybody care to have a punt at how many terawatt hours we have in the UK? Or here's a clue, it's not terawatt hours, it's gigawatt hours. The answer is 30 gigawatt hours. So we have 1/30th of a terawatt hour of pumped hydro in the UK at the moment. And we need about, well, at least 50 terawatt hours, probably more like 70 terawatt hours. So we're 1,000 times too small in terms of what we can store. So it's tempting to think from the Royal Society report then, these costs that it predicts, even pessimistically, would be 92 pounds per megawatt hour, and very optimistically, they could be 52 pounds per megawatt hour for energy onto the grid that's exactly at the time that we want to use it. So these look at very, very appealing numbers with the assumptions. And so it's tempting to think that we have found the answer. And probably Professor Chris Llewellyn-Smith considers that we have found the answer, that this is the answer. And my message to you is, this is not the complete answer. So that's a good answer, but there's more that we could and should do. And so the rest of this is really about making the case for energy storage in different timescales. And this is a chart. I think many academics have a kind of signature graph, and this is going to be my signature graph. This will be the graph by which everybody will say, oh, that's Garvey, because it picks out that there are 4 separate time spans of storage. And I won't deal with them in strict order. I'll deal with them starting from the long end. At the very long end of things, the only thing that matters is how much does it cost per unit of energy that you can store. And for that purpose, the only candidates are fuels, like hydrogen. Hydrogen is a fuel, ammonia is a fuel, dimethyl ether is a fuel, etc. Synthesized fuels, or fuels that we can store. Biomass is a fuel, but it's only those things. You can store them, you can store vast amounts of energy in the form of fuels, and then you can release that when you require it. And that will dominate the very, very long durations of storage because it has low costs per unit energy. And then the next thing I'll deal with is range number 2 here, the short duration storage. And down here, what matters is the cost per unit power, not the cost per unit energy. So up here, it was cost per kilowatt hour, and batteries would cost you about £200 per kilowatt hour, and hydrogen will cost you about 50 pence per kilowatt hour. And down here, what matters is the cost per unit power, cost per kilowatt. And batteries are the right solution for this thing because they have a very low cost per unit power. And in the middle here, between these two, is sandwiched a whole set of technologies. Most of them are mechanical, and I refer to them as medium duration energy storage solutions. And they are a good compromise between reasonable cost per unit energy and reasonable cost per unit power. They're more expensive per unit energy than fuels. So ultimately, they lose out to fuels on very long timescales, and they're more expensive than batteries and electrical systems per unit power. So they lose out if you go short enough in time. But for a large swathe of timescales in the middle, and that's typically between 4 hours and 200 hours, these are the best solutions. And they're getting squeezed out. The policymakers are think, well, we've got hydrogen for the inverted commas long duration, we've got batteries for short duration, so we've solved the problem. Wrong, we haven't. We're going to cost the country a bit more money than we need have cost. And to give you some idea of how much that is, you can think forward and say, well, what if we did run the whole country off renewables? Then what you would do is you'd make a plot. You would suppose, what's the demand going to be like in the future for a 10-year period, let's say? And you'd say, I have to meet that demand somehow. So you would draw a plot of demand over 10 years, and then you draw another plot for the supply over 10 years. And you would say, right, well, what's the difference between demand and supply? And I call that net demand. So the amount of electricity that the consumer wants to gobble up, take away the supply, is net demand. And when that's positive, we have to be taking energy out of storage because it has to come from somewhere. And when it's negative, we can put energy into storage. So we're going to analyze net demand and see how it's distributed over time. And if you do that, you find, well, this blue waveform on the left is obviously going up and down across zero quite a lot. But we're going to focus on the times when it goes positive. So it goes above zero. And we're going to look at how long for each lump that goes above zero, how long is that lump? And sometimes it'll be short. So, for example, this little bump here is just under an hour. And we're going to put that in a first bin that I'll call short duration storage. And then anything that's longer than 4 hours, but shorter than 200 hours, I'm going to put it in a second bin, and I'll call that medium duration energy storage. And any one of these lumps that lasts more than 200 hours, I've got another bin for that, and I'll call that long duration storage. And I'll just add up the total amount of energy in the short duration bin, the medium duration bin, and the long duration bin, and I'll see what the answer is. And the answer is amazing. You see that 92% of all the energy that comes out of storage has to go in these medium duration bumps. So it means that the optimum solution here for those things is not batteries, and it's not hydrogen. You can do them with batteries and you can do them with hydrogen. It's just not the optimum thing to do. So to make this point, alongside the Royal Society report, I wrote some code, computer code, and I call that code NSTORE-SIM. And NSTORE-SIM has a very obvious name. It's for simulating a system that has got N stores in it. And it enables you, therefore, to say, well, how cheap or expensive can this system be? And it's a set of code that's fully open source. Unfortunately, you have to have MATLAB to do it. The Department of Energy Security and Net Zero criticizes me for the fact that you have to have MATLAB to be able to run this, but it's a free gift to society, so I don't feel bad about that. And if you go to this link, you'll find 4 videos about how you can use that code, and also some documentation. And it solves a very simple problem. It says, suppose that we are going to consider a future energy system that has a mixture of storage types. So it's got some hydrogen, of course it will do, and it's got some batteries, of course it will do, and it's got some mechanical solutions as well in the middle. Then what's the cheapest system that we can run? And what you always find is the cheapest system has quite a bit of energy running through the mechanical types of storage. And in fact, I'll steal my own thunder, about 2/3 in the cheapest, in the cost optimal system, you find about 2/3 of all the energy passes through these mechanical type systems. So it's a very simple concept. You have a vector, a set of numbers, which I'll call P, that tells you how many terawatt hours of hydrogen do you have, how many gigawatts of input power do you have for the hydrogen, how many gigawatts of output power do you have for the hydrogen, then the same thing for mechanical systems and for batteries and anything else you care to consider. And then you just give the problem to an optimizer, and the optimizer pops out and says, well, here's the best cost that you can get. So it's quite simple to understand how this works. It's particularly simple to understand it in the case of when there's only one energy store. So if you imagine you're going to do everything with hydrogen, you need to start with this information. You need to start by saying, what will the demand be? What electricity will people want over a period of time? And then what will the profile of renewable generation be? And we're going to scale that up. So we'll call 1 unit of renewable generation is exactly the same amount of energy as we consume. So imagine we're going to consume, let's say, 600 terawatt hours per year in future. Well, we definitely have to generate more than 600 terawatt hours. So we'll call 1 unit is 600 terawatt hours. And we have to have information about the different energy storage options. We have to know each turnaround efficiency, the ratio between what comes out and what goes in. And we have to have a criterion for what acceptable means. So acceptable to me not only means meeting all the demand, but making sure you've got a little bit of extra in every single hour over that period. So, you know, you don't want to sail very, very close to the edge of the cliff. You want to keep some distance away from the edge of the cliff and still be working. And this code, NSTORE-SIM, can discover an approximate cost optimum point. So with one energy store, you're actually playing with 4 different parameters, but 3 of those are independent. So 3 of them you can pick, and the 4th one is a consequence of the other 3. The first one is the input power, G, and the second one is the output power, H. The third one is the capacity, the volume of storage that you've got. And the 4th one is how much are you going to over-generate? Because you may have to over-generate by greater or lesser amounts depending on the values of these first three. So as long as the first three parameters there lie within reasonable bounds, you will be able to find some minimum value of X, this over-generation factor, that makes sure your system is good. And then you can put a cost to the whole system. So it's quite intuitive how you could solve that problem. If you want to test whether a particular combination of the input power, output power, storage volume, over generation factor is acceptable, you've got to march through every hour in turn of a long series of hours. Now, I said earlier on that Christopher and Smith modeled 37 years, and if you calculate it out, that's 324,000 hours. So you step through 324,000 hours each time. You initialize the amount of energy in, there's only one store. They probably say it's 70% full, and then you march through time. And if there's a shortage of energy, you take some energy out of store. And if there's too much energy, you put energy back into store. And when you put the energy back into store, you have to throw away some because there are losses associated with putting energy in and taking it back out again. So this is a very easy problem. There's no scheduling to do here. You don't have to choose which store shall I put my energy in, because there's only one store. You don't have to choose which store shall I take my energy out of, because there's only one store. And this problem of figuring out whether the over generation is sufficient is completely easy, because you just try a number like over generating by a factor of 1. That's definitely too little. Over generating by plus 60% is definitely too much. So you start with those two, and then you say, well, I'll try halfway in the middle. Is that too little or too much? And if you get the idea, it's an interval halving. You can just say, if that was too much, forget about 1.6. This is now my new upper limit. And then I'll try 1.15 and so forth. So you do this halving of intervals until eventually you get quite an accurate estimate of how much over generation you need. And this is, well, there are two plots on here. The one on the right-hand side is from the Royal Society report, and it uses one dependent axis, which is the volume of storage you need, the size of the hydrogen store, and it uses two independent axes, which are the input power and the over generation factor. And the graph on the left-hand side comes out of NSTOR sim, and effectively it has the same information, but it's turned the axes around. So it's treated over generation as a dependent variable, where the Royal Society report considered that to be an independent variable. But effectively, in both cases, you draw a surface, and any solution that's above that surface works, and any solution that's below that surface doesn't work. And somewhere on that surface, there is a point that has the lowest cost. And all of the points on that surface have known cost. So it's easy enough to solve that problem. And then we can go to imagining what happens if the system has two stores, and the problem is almost the same. So with two stores, you now have two different input powers, G1 and G2. You have two different output powers, H1 and H2. You've got two different capacities of storage, V1 and V2, and you've still got only one over generation factor, because you have to, there's only one number that describes how much more electricity do you have to generate in a year than you consume. And so if you have a set of 7 numbers now, you can find out whether that set of 7 numbers is acceptable by doing much the same thing as I described in the case for one store, which is initialize the energy in each store so that it's something like 70% full, step through each hour, 1 hour at a time, out of 324,000 of them. If there's too much electricity during that 1 hour, we're going to put some into storage, but which one? I'll come back to that point. And if there's too little energy, we're going to take some energy out of storage, but which one? So that question of which energy store do you fill at any one time and which one do you empty at any one time is called scheduling. it helps you to decide which one you should do. And the scheduling problem has basically been solved, or at least there is a reasonably good solution for it. And the solution for that problem is down to a retired academic from Heriot-Watt called Zachary, who effectively says, well, the stores should operate on the principle of greed. And at any one time, you say that there is a marginal value for any one store of receiving energy and a marginal cost for dispensing energy. And at any one time, you take in the most valuable energy, or you take in energy where it's most valuable, and you give away energy where it's least valuable. Now, this plot here shows you those marginal values. So the blue line on the top, the blue curve on the top, shows you that if a store is this represents the marginal value for discharging a store. So you see hydrogen will discharge, but it has quite a high value for discharging, and below it there's a storage called ACASE, that's adiabatic compressed air energy storage. That's most of the time it's lower than the value for hydrogen. So most of the time you'll try to discharge from the compressed air energy store, except when it's very nearly empty, at which point it's got a higher value than the hydrogen. So when the air store becomes fairly empty, you would prefer to discharge from hydrogen. So what this approach does is it makes sure that you keep the stores away from the end. The stores never get too empty and they never get too full. And that's a very sensible thing to do. And more details in the paper by Zachary. And if you can do 2 stores, you can do any number of stores. So you can in general do N stores, and the procedures are just a logical extension. You can test whether a set of N stores either will or will not work by doing the same process of stepping through every hour in a series of 320,000 hours. If there's too much energy, you put some into store, and you decide which store you put it into based on that algorithm by Zachary, and you decide equally well if there's too little energy, you decide which store to take energy out of, again based on that. And so this enables you to say, if you pick 3 N values that describe the stores, what's the smallest amount of over generation that you can have, and then therefore what is the cost of that energy system. So here's an animation that shows you 3 different energy stores being used in an energy system. And I'm going to probably run this twice, but let me tell you first of all what's going to happen and what these graphs mean. The graph on the top represents a fill level for each one of 3 stores. So what you see at the moment is that all 3 of the stores are empty for nearly all of the time. And the reason for that is we have got no overgeneration at all. We're only generating exactly as much electricity as is being consumed, and the stores are just empty all the time. And in fact, there's a shortfall. We're not able to meet demand, and that shortfall is represented in the plot at the bottom. So when I play this, the vertical axis on the bottom plot shows you how big the shortfall is. The horizontal axis on the bottom plot shows you how much we're over generating. And I'm going to start by over generating nothing, effectively. I'm going to start with only generating exactly the same amount as is required. We know that's not satisfactory. And what you will see is that this red dot will march down this curve, and the shapes of these fill levels will change. So let me play that once. So as we're now generating more and more electricity, you see these curves starting to lift off. The red, green, and blue curves are starting to lift off the bottom. And the green curve is going up and down madly. It's doing most of the cycling. And the blue curve is behaving the slowest. And now, just now, all of the curves have lifted off the bottom. And what that means is that none of the stores ever got empty. And it's only at the point where no store is completely empty that you know that the system works. Because if any one store was getting close to empty, it would try to not put out any more energy, and it would try to tell you to take energy from the other stores. So basically one can't empty without them all being empty. And if any one of them is empty, it means you've run out of electricity in store. So if you have enough over generation, you eventually find that there's a system there that does work. Now, the 3 stores that I put in here, the first one is wind integrated storage. And I'm going to spend a few minutes about what that means. Integrating storage with wind turbines in a really tight way. The second one is compressed air energy storage. That's just pressurizing air and putting it into a cavern. And the third one is hydrogen storage. And it's worth looking at these numbers on the right-hand side. The wind integrated storage will have efficiencies of 80% or more. Very, very high turnaround efficiencies for the wind integrated storage. Compressed air energy storage probably having efficiencies in the mid-60s, 65%, maybe 68%. And the hydrogen storage has a terrible turnaround efficiency because there's chemistry involved, and there are quite radical changes in the energy form, but it's very cheap to store energy in there. So they're all worthwhile having. They just have different features. Oh, didn't mean to do that. Well, let's let that run again. So you see the over generation factor increasing, and you see the store fill levels tending to rise up above 0. And it's only when they lift off above 0 that you know that we've got a system that works. And if you look here, this system here is now able to work with 19% of over generation, right? So that's much less than the 30% that I said at the start you would need with an all hydrogen solution.
But Seamus, just going back then to that took 35 years to achieve. Is that?
No, this is what I'm doing is I'm simulating the energy system over 37 years.
Okay.
So I keep on simulating the same 37 years.
Right. Okay. So how long would it simulate to get that storage? Lesser years than that? Could it be 5 years to get that?
Oh, to build the storage.
To build the storage.
So different stores take different lengths of time to build. That's a very important point. Hydrogen storage.
You're condoning the practice of having all 3 operating together here in some mix.
I haven't dealt with the transition, so you're raising a hugely important point. We have to get from here where we have effectively no storage at all to a new system where we've got a lot of storage. And if making salt caverns, which is the basis for both compressed air energy storage and hydrogen storage, takes years. It takes 4 to 10 years to make a salt cavern. So you can't just flick a switch and hope that your salt caverns appear overnight. They don't. This isn't thinking about the transition. This is thinking about where are we trying to get to. And as soon as we know where we're trying to get to, then we have a separate question to know how do we get there, which is a rather more difficult question, in fact. But I'm not modeling that. So this is just looking at 37 years as a representative set in time. Okay, so what you can do then, if you understand the basis of how that calculation works, is you can say, well, let's consider different blends of storage. And I'll just trot through these blends of storage fairly quickly. So let me start by saying, let's consider hydrogen storage only. It has a turnaround efficiency of 41%, approximately, if you go electricity in and then electricity back out again. And it has these values for how much the input power costs, how much the output power costs, and so on. How much does it cost to make the caverns and so forth. Down here, there's a value that's really quite important, particularly for hydrogen. It's the cost you will associate with running down the store. So if you imagine that you had 80 terawatt hours at the beginning of a long period, and at the end of the long period, you've only got 10 terawatt hours left in that store, you took a lot of energy out of that store and it wasn't free. You have to pay for that, and you have to pay for it at some rate, and you have to decide what is that rate. And I've put a rate of £60 per megawatt hour as being something somewhat representative. So these are the costs for energy delivered to the system if you only use hydrogen. And then we're going to look at a few different other possibilities. So you could blend in some compressed air energy storage with the hydrogen. These are the numbers that are used in the Royal Society report. The power with compressed air is cheaper than for hydrogen, but the storage is about 6 times more expensive. It's more expensive per unit energy stored. And now you can see some interesting combinations that if you think about compressed air on its own as being the energy store, it's more expensive than hydrogen on its own. And that's not surprising. But blend compressed air with hydrogen and you get a solution that's cheaper than either one of them on their own. So this is showing you save £2, about £2 or £3 per megawatt hour if you blend compressed air with hydrogen. And then I'm going to blend in this wind integrated storage as well. With it, this time I've put a higher efficiency on it. It has very low costs per unit input power, and etc. The other features like that. And you find that you reduce costs still further. Now you couldn't use wind integrated storage all on its own, but you can use it blended with compressed air and blended with hydrogen. And you see it's saving about £1 per megawatt hour if you blend that in as well. And then you think about, well, what about gas-fired generation with CCS? And you can treat this as an energy store because you can think about gas as being a huge volume of storage that starts out full. You can never put any energy back into it because you can only consume from it. You do have to pay for the deficit. You do have to pay down here for how much you've depleted that store over its whole life. That's the main cost. And you have to pay for the generating capacity. So some of the other costs are simply not applicable, but you have to pay for your gas-fired generation and you have to pay for how much you've depleted your store. And I'm not saying that £200 per megawatt hour is how much you have to pay. I'm just saying that's a possible representative number. And what that tells you is that, okay, this adding in gas-fired generation gives you results that are better than just using hydrogen on its own, but not much better. They're slightly better than using hydrogen on its own, but basically they are not better than using a blend of hydrogen and compressed air. And so if the numbers that I put in are representative, and not asserting that they are, but if they are, there is no place for gas plus CCS. Stuart is going to have things to say about that. In my opinion, there may be no place for gas with CCS. So it's all about, is there a case or is there not? On this model, with those costs, there's not a place. Now, where there is a place is in the transition between now and getting us to net zero, because we are going to struggle to do that with making a lot of carbons. So that's basically the first piece that I want to say, and I've got about 10 more slides that I would like to tell you about afterwards. But my three assertions here are, firstly, we can run an affordable net zero energy system in the UK. Hydrogen stored in caverns is going to be the backbone of that, so I don't dispute that at all. And we're going to need a few tens of terawatt hours of that storage. But if we blend different storage types, we reduce costs, and that reduction is in the order of 5%, which on some scales 5% isn't much, but when you're spending £20 billion a year or 30 or 40 billion pounds a year, which is the order we're spending on energy, 5% of that much is a lot of money. So that's my part one, and then I hope you'll bear with me to just hear a little bit.
Yeah. Any questions for David? Go on, Sophie.
Yeah. Thank you for explaining everything. Trying to get on to the next bit, but I was wondering, why is the adiabatic case more expensive for the storage process than the hydrogen? Is it both salt cavern based?
They're both salt cavern based, but essentially the ratio between how much energy you can store in the form of hydrogen in a salt cavern and how much you can store in the form of compressed air is about between 14 to 1 and 20 to 1, depends on the pressure. No, it's not because you had much higher pressures. It's because you can set fire to hydrogen. You can release the chemical energy in hydrogen, and there's no chemical energy at all in air. All you can do is let it back out into the atmosphere. So you're not storing any chemical exergy. And in fact, most people, I was quite surprised that the ratio is only about somewhere between 14 and 20 to 1. But the reason for that is hydrogen has very low density. So even though it has a very high calorific value, it's got appallingly, it's good in some respects, It's very, very low density, so it's 9 times less dense than air, and that means you don't actually get many cubic meters or many kilograms of hydrogen into a cubic meter at a given pressure. And for calibration, if you put natural gas in the same cavern, you get 4 times as much energy in the natural gas cavern as you do in the hydrogen cavern, because you actually put more hydrogen in it, ultimately, with carbon molecules, unfortunately, holding it all together. So good question, but it's mostly got to do with the amount of cavern that you need.
Thank you for the talk. It's been interesting so far. We thought about how when you're storing hydrogen and getting extracting your hydrogen back out, the balance between extracting it as and converting it back to electricity, or just extracting it as a gas, and how that would affect the model.
Yes, it can only be. So the Royal Society report only thought about electricity in, electricity out, and it's then therefore it put a constraint on the system. It said we're only going to think about that, and if you relax that constraint as a general principle, you always do better. You know, constraints always worsen a system. If you relax that constraint and you say there are other things that we could use that hydrogen directly for, we were talking with Stuart, well, what else can you use it for? Well, you can use it in steel making, and you can use it in cement making, perhaps, and you can use it for making ammonia. Well, you do anyway, use it for making ammonia. And people were talking 5 years ago about possibly using it for heating homes. And then you realize that that's utterly, in some respects, utterly bonkers, because if that was green hydrogen, you take let's say you take 100 units of electricity to make green hydrogen, you end up with 70 units of energy in the form of green hydrogen because it's 70% efficient. You then set fire to that in your house and you release 70 units out of 100 to start with. Is that okay? Whereas if you used 100 units with a heat pump in your house, you'd end up with 400 units of heat in your house. So that the ratio between 400 and 70 is more than 5 to 1. So on that equation, it looks just crazy to think about hydrogen for home heating, and most people get that far. In reality, if you say we're going to store some hydrogen, and then we're going to have to take it out of storage and use it back again, there is an argument that says it's not that bad to use it for heating if you're taking it out of storage. So if the only hydrogen that you use has come directly out of storage, you get the flexibility benefits of that. And I apologize in advance for inflicting this complete aside on you, but when we think about heat pumping, we always think about electricity driving the heat pump, but you can actually have a heat-powered heat pump. And I have a postdoc working on the idea of a heat-powered heat pump. So you can get a heat multiplier. And I invented this and then realized that Lord Kelvin had invented this in 1852. And he published a paper on it, and he actually called it heat multiplier. So it's completely straightforward thermodynamics to take hydrogen, bring it into a house, and then use it to not only provide heat for the house, but actually do some heat pumping. And I do think that could make a significant difference. So in that sense, I think the case for hydrogen gets stronger, and I think you made a very good point. This is a constrained view. Benjamin Hall has his hand up.
He does. Ben, can I ask you a question?
Yeah, it was just a question, really, clarification. You mentioned wind integrated sources there, and you might have said this earlier on in the presentation, but by that, do you mean battery storage and pumped hydro at the site of the generation? And do you see a role for marine pumped hydro as well in the UK?
This is exactly the subject of the next 10 slides. So I wanted to whet your appetite. I wanted that question. So I'm going to answer that question.
That was pre-planned by me. Can I ask one then before you move on about salt caverns?
Yes.
Because there's been a lot of talk about actually where we can store compressed air, even it's a great site for storage of hydrogen.
Yeah.
Because it's so impermeable to
it's fantastic.
small molecules of hydrogen out. But we don't have many places in the UK that have salt caverns that are actually suitable. So there's the Cheshire Basin and the portions of that. There's down the road here at Teesside, which has some salt caverns which are currently being
used for hydrogen.
And then we then got to go offshore, probably the southern North Sea, maybe the northern North Sea. Which is, getting into a terrain which is much deeper, much more complicated. So if there isn't enough salt caverns, what's the other potential storage?
You can use hard rock, but I think there is enough. There's enough salt. So there are not enough salt caverns in existence. I mean, the reason why most salt caverns exist, and most of them are in Cheshire, is because INEOS, or whatever, ICI as it was then, wanted to get sodium and chlorine probably particularly, out of the ground, and therefore they solution mined a lot of salt caverns that didn't have any other purpose other than to just take the salt out and decompose it. There is actually quite a lot of salt in the UK. We're in fact, I said earlier on, we have a uniquely rich resource in wind. People don't really appreciate how fortunate we are in salt as well. We are very, very fortunate in salt. There's also, Germany is very fortunate in salt, and Poland is very fortunate in salt, but we are not poor. And off the south coast of Portland, where's the Portland Peninsula?
Wessex Basin.
Wessex Basin, thank you. Wessex Basin is particularly interesting because there's very deep salt in the Wessex Basin, and very deep salt is very good because you can then get very high pressures, and it's really exciting what you could possibly do in the Wessex Basin. So it's a question that has been asked: is there enough salt? And Chris Llewellyn-Smith did ask that question. He asked BGS to do careful studies, and BGS has published some papers. I've been a co-author on some of those actually, about compressed air. Is there enough? There's no doubt at all that you could do 50 terawatt hours of storage in hydrogen within salt in the UK. The key point, I think, is that depending on how hard you run your pumping, your solution mining, it's going to take you 5 years upwards to make a cavern. And so you don't get from 0 to 60 miles an hour in 4 seconds. There's
to link it to that then, Seamus, do you think it's a better way to go in what Centrica are taking in reconverting the rough gas storage site to be hydrogen storage?
I do think
source.
Completely agree with that.
Joe and I both know that immense problems associated with the rough site to store hydrogen in it.
Okay.
It can be very quite leaky.
If you can store hydrogen in it, that would be absolutely fantastic. It would be
looking at what, 10 terawatt hours of energy storage in the.
Okay, well that's an enormous lump. It doesn't get us home and dry. We need several tens, but it's a big difference. There is one rather interesting thing though. Shortly after the Royal Society report came out, a bunch of people from the Global Warming Policy Foundation decided that they would take some pot shots at it. And I've been in a conversation with these people, antagonistic conversation I might add, ever since. But a part of their suggestion was about how much energy it took to form the salt caverns. And it's a staggeringly, in some sense, a staggeringly small amount of energy. But of course, as a fraction of 100 terawatt hours, let's call it that, it's only 0.25%. But 0.25% of 100 terawatt hours is actually a lot of energy. And the interesting thing is that making the salt mines themselves is a flexibility resource, because the machinery that you need to do solution mining is just pumps. You drill the hole, that's an expensive bit. And then after that, but that's not where most of the energy is. Most of the energy is actually in pumping the water over years to remove the salt. And you can switch pumps on and off. Pumps are cheap. They're not high pressure pumps. They're quite cheap. So the whole process of making the salt cavern is actually a flexibility resource that can help us a little bit in the end. I'm going to answer Ben's question then. So I want to spend a couple of slides talking about what I mean by wind integrated storage and integrating that, and really why I'm here, why a mechanical engineer cares about any of this stuff anyway. I only care about this because of wind integrated storage, if the truth is told. Here's a few statements. Wind is a mechanical energy form. You turn a rotor that goes round and round. The energy storage technologies best suited for the durations that we will have are mechanical in nature. They're compressed air, pumped thermal, gravitational potential, pumping water up a hill, and a few other things like compressing carbon dioxide. About 25% of all the energy that we will collect by wind turbines is going to pass through storage. There's no doubt about that. And so if we just think about storage as being something completely separate from wind turbines, then for all the energy that passes through storage, we're going to transform it from mechanical energy, which is the rotor turning around the wind turbine, into electricity, back into mechanical energy to put it into storage, and back into electricity to take it out of storage. And that doesn't make any sense to me. It seems to me that for 25% of the energy that we collect with wind turbines, we should do something a little bit more clever. And if you represent it schematically, this is the conventional thinking. This is supposed to be a wind turbine rotor on the left-hand side. Sometimes there's a gearbox, sometimes there isn't, doesn't matter, really. There's either a gearbox and a generator, or else there's a direct drive generator with a lot of complicated power electronics behind it. But one way or another, it's either an electrical gearbox or a mechanical gearbox. So you convert your wind power into electricity, and then you use some of that electricity. In fairness, you use about 75% of it directly. The consumer uses it. And the other part of that, you have to convert into something else and convert back. And I don't think that's a good idea. So I think that it would be better to make wind turbines that look like this. So you take your wind power and you capture it in a form that you can actually store, or at least some of which you can store. And if you want to consume it, you convert it into electricity straight away. And if you don't want to consume it, you put X into storage, and then you fetch it back out again later on, and you convert it into electricity. And generically, I call that generation integrated energy storage. So it's where it's effectively the same thing we do with coal-fired power stations right now. We gather energy in a dense form right beside the generator, and then we only convert it to electricity when we want it. We keep it there, and we convert it to electricity. So it's putting the storage before generation instead of after generation. And the advantages of this are threefold. The first two are the big ones. If you have fewer energy transformations, you have fewer losses or smaller losses. You also have fewer pieces of power conversion equipment, which is cheaper. And if you do it at a wind turbine farm, a wind farm, you use the transmission lines of the wind farm better. And the transmission lines are a significant chunk of cost, so that's good. But you wouldn't have to integrate the storage to get the third advantage. You only have to do that for the first two. And this is a sort of chart of throughput efficiency. This chart represents the ratio between all the electricity you get out of a wind farm, let's say, and all the work that you put into the wind farm, depending on how much you pass through storage. Now, existing wind turbines are very efficient. Their transmission system is very efficient. So if you look at how much mechanical work comes into the wind turbine rotor, and then say how much goes out as electricity, 96%. Fantastic. And the things that I'm proposing will not be as efficient as that for just making straight electricity. So if you want to consume electricity directly from a wind turbine with none passing through storage, you should use a conventional design, no question about that. But if you are passing energy through storage, the red line here shows you that obviously if you pass, let's say 10% of it through storage, and the storage has losses of 30%, then you're going to lose 30% of 10%, which is 3. And so you get an overall decrease in performance. And the wind integrated storage does better if a high proportion of all the energy for those wind turbines passes through storage. And so you might say, but you've just told us only 25% is going to pass through storage. So actually I've told you 25%, which means that the red curve looks better. But what I'm not saying to you all wind turbines should have this. I'm saying to you only about a third of all wind turbines should have this, and those wind turbines should manage most of the storage. And in that case, you're really onto a winner. Because if those wind turbines are putting maybe 80% of their energy through storage, you are this much better off than you would have been with a conventional arrangement. And there are some easy ways. This goes to Ben's question directly. How can you do that? Well, you could get wind turbines to pump water up a hill. And it's technically possible. It's a terrible idea. The reason why it's a terrible idea is that if you have wind turbines anywhere near a hill, they should be on the top of the hill, not on the bottom of a hill. And you can't suck water up a hill because atmospheric pressure isn't enough to push. You know, if you can only suck water up 10 meters because that's the same as atmospheric pressure. So you can't suck water up a tall hill. So you could put your wind turbine at the bottom of the hill, but then it's going to be a terrible place for a wind turbine. So people have talked about that, but it's a terrible idea. It's technically possible. You could do what I first thought about in 2005, which is get your wind turbine to compress air and then keep that air somewhere. And there are interesting challenges with that. The main challenge with that is that air has a very low pressure, same challenge as pumping water up a hill. Air has a very low pressure. And so in order to use up all the energy that a wind turbine gives you in one rev, you have to suck in a vast amount of air to compress it. And you can't direct drive an air compressor basically, because it would have to suck in too much air. It wouldn't fit on top of the wind turbine. So the third possibility is you could convert all the rotor work into heat. So troglodytes knew that if you take a stick and you rub it against another stick, you can convert work into heat and eventually you can make fire. Well, in effect, this proposition is you could take all the rotor work and just make high-grade heat with it. And it's not great. It's not as bad as people first think, because it is high-grade heat. So this will be heat at more than 300 degrees. So it's not terrible, but Mr. Carnot efficiency tells you you're never going to get back more than about 50% of what you put in. So it's limited in how good it is. And the best solution is my solution, which is pump heat. You can pump heat from a cold place to a hot place, and then you can let that heat go back. And I call that system wind TP, and a couple of slides on that. There are two other possibilities. One of them is called energy, or is based on energy dome. An energy dome is an energy storage proposition where you compress carbon dioxide so much that it turns into a liquid, and then it's very compact. It's brilliant, and it's also liquid at close to ambient conditions. You can liquefy carbon dioxide very nearly at ambient temperature, -30, I think, or something like that. And then you expand it again. The big problem with this is you can't just let it back out into the atmosphere. You have to hold it somewhere so that you can compress it back into a liquid form again. And I actually did some work in 2011 about bags for storing compressed air underwater, but you could equally well use them for storing carbon dioxide underwater. So I think there's some possibility that you could do this with carbon dioxide as well. And you could do a variant of the high view power. The liquid air energy storage is also possible, because pardon me, most of the energy that you use to liquefy air is just compression energy. So I'm going to run out of time, but I want to just give you just the very edge of what wind TP is. Wind TP is wind integrated storage, but it's implemented thermally. It's a power transmission system for wind turbines that takes in work from the rotor and makes electricity the same as any other power transmission system, but it uses a reversible thermal pumping cycle. And you can get about 100 hours of rated output at marginal costs, much less than the wind turbine itself. And here I'll just explain the key idea. There's already an established idea in engineering practice about a hydraulic transmission in a wind turbine. And with a hydraulic transmission, you have a wind turbine rotor that drives a very slow, very big hydraulic pump. And that sends hydraulic fluid round in a circle, in a loop. And on the other side of that loop, there's a hydraulic motor that takes out the energy from the hydraulic fluid and it drives a generator. So all things considered, you can call this a hydraulic gearbox. And it's a very small extension to that to say, take out the hydraulic fluid and throw it away and put in a gas instead of the hydraulic fluid. And now you're, instead of a pump on the left-hand side here, it's a compressor. And instead of a hydraulic motor on the right-hand side there, that's an expander. And when you raise the pressure of a gas, it gets hot. When you drop the pressure of a gas, it gets cold. And you can use this to suck heat out of the hot side and suck coldness out of the cold side when you have too much wind energy, and you can do exactly the opposite when you've got too little energy. You can put it back in. And I've got some animations, but I don't want to use up more time than I'm allocated. So I'm not going to show those allocations. Let me just escape from the presentation and see whether I can jump to conclusions. Well, I'm going to do this. I'm in the process very slowly of building this thing. The picture on the right-hand side is me standing beside what my colleagues refer to as the stainless steel hedgehog. And the stainless steel hedgehog is now built up into a machine that has a bottom part and a top part. The right-hand side is the CAD image. The picture on the left-hand side is was an incomplete version, but in fact, I've got the funding in a research grant at the moment to finish this as a compressor. This is a prototype for the primary compressor, and it will be finished in February. And I hope that you will hear in February that I have built the most efficient compressor in the world. And I think you will also find it's the most expensive compressor in the world per kilowatt. And that's perfectly fine, because wind turbine transmission systems are expensive anyway. So it's not like it's not for compressing air, it's for a wind turbine transmission system. This is my final conclusions then. Repeating the first bit, we are going to have to store a lot of hydrogen in caverns for a net zero UK. That's what the Royal Society report says. However, we are going to use a lot of medium duration. We should use a lot of medium duration storage. And that should process about 2/3 of all of the energy that passes through storage should go through that, not through hydrogen. And we can expect cost reductions of more than 5% compared to just using hydrogen. This fourth bullet point is an assertion. So I can't prove it. I just think it's right. I think wind integrated storage could be a major economic opportunity for the UK. And I think, and I can explain why I think this, that it could represent more than £1 billion a year of opportunity to the UK. One way that you can do this wind integrated storage is using WindTP. And I've given you a brief introduction to a tool that elucidates the role of medium duration storage, which is this link here. And at the end of all this are a few little adverts. I'm running the UK Energy Storage Conference in Nottingham in 2024 in April. It's really coming up very soon. And there are some past links about events on medium duration energy storage, including this one, which is happened in January the 12th. And there's a fabulous conference coming up in Bedford in Massachusetts in July. Thank you very much.
Thank you. Wow, okay, lots to take on board though, isn't there?
Yeah, I had to leave out a lot. Sorry, Stuart.
Just very quickly, because I am aware we're going to get kicked out of here in a minute by sociologists. Why not hydrolysis to create more hydrogen? Why are you wanting to create other energy sources? Why not create the hydrogen and then pump that back into the system?
You can do that because you lose 60% of all your energy.
Yeah.
You lose 30% right there when you make hydrogen. You lose another 30% converting it back.
Okay.
If you wanted to use, if you were providing the hydrogen for ammonia, then hydrogen was what you wanted, and you had to make that anyway. So that's a great
product.
Yeah. Okay. So as long as if you want to feed ammonia plant, and we do need to feed ammonia plant, but we don't need that much ammonia.